Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so good morning, everyone. This talk will be on a part of the thing I'm doing during my PhD on improving efficiency in range querying in distributed online games. So massively multiplayer online games, or MMOGs, offer a vast virtual environment which players are able to freely explore. Any player in the game is able to interact with virtually any object or other player in the game. However, at each given moment, it only sees objects that are located inside the so-called area of interest that surrounds the player. And the MMOG application has to guarantee responsiveness of the area of interest for each player. That is, all objects that are located inside the area of interest of a player should be displayed with very low latency. A range query is a basic operation that allows to retrieve all the objects or update all the objects located inside a particular area of the game space. Therefore, range querying is very well suited to retrieve the area of interest of players, and in the context of multiplayer online games, should be very responsive. Massively multiplayer online games has been very popular over the past few years. Here we can see a plot that showed that the cumulated population of MMOGs has reached 16 million in the 10 years that followed the emergence of MMOGs. The market income has been estimated to $2.7 billion in 2010, and it's still growing. However, paradoxically, the main problem of current MMOGs is that they don't scale. To support the huge amount of players, the MMOGs split the whole population into separate gaming instances, called shards, and each shard is held by one server. The populations that are located in different shards are unable to communicate with each other. And each shard's population is limited to only a few hundreds of players, which results in a poor gaming experience. Moreover, since the popularity of the shards is not uniform, some of the gaming instances are very popular and almost overloaded, whereas others are left almost empty, which leads to a substantial financial loss for the game provider. Such a poor architectural choice comes from the fact that the key requirement of MMOGs, the responsiveness of the display of the area of interest, is pretty hard to ensure at large scale. The architecture has to provide very low latency for some key mechanisms of MMOGs, such as routing, range querying, or publish-subscribe, which is hard to do at large scale. Also, security is one of the main concerns, even if it will be outside of the scope of this talk. So these are complicated challenges. Over the past few years, a whole lot of academical work has been addressing these problems, sometimes with very good ideas. But still, all the existing MMOGs are still server-based, which means that there is virtually no impact of these academical works on the market. I state that these such few impact comes from the fact that only a few solutions proposed in the state of the art are really adapted to MMOG workloads. So, in this talk, there will be two parts that will explain two main contributions of my work. In the first part, I will describe how we can improve routing in peer-to-peer MMOGs with non-uniform peer distributions. That will be main part of the talk. And for the part 2, I will explain you my current work, which is density-aware range partitioning for scalable low-latency range querying. So, first part on the peer-to-peer MMOGs. One of the ways to address scalability in MMOGs is to use peer-to-peer range query overlays. Such range query overlays range partition the game space. That is, each peer has coordinate in the game space and stores objects that are the closest to its coordinate. And two peers that are close to each other in the game space will be neighbors inside the overlay. So here we have an example of a partition of the game space following a Voronoi diagram and the underlying Delaunay graph. Such kind of peer-to-peer overlays are extremely well suited for MMOGs because they preserve data locality, and therefore they enable efficient range querying. They also inherently provide decentralized greedy routing, and the peer-to-peer paradigm ensures that the overlay has a good fault resilience and low cost for the game provider, since the whole architecture relies on the players. There are a few examples of such kinds of overlays in the state of the art. Our goal is to improve the routing process inside the range query overlays. Since they preserve data locality, the routing process is not needed for local interactions of the player. However, it is still needed for a few key mechanisms of MMOGs. Namely, the efficient routing is needed when a peer joins the overlay, since it has to be routed to its coordinate. We also have load balancing, because some areas of the game space may be overloaded and an underloaded peer may be asked to join the overlay in that particular point, which will incur routing. And also, many existing MMOGs provide teleportation to their players, because the game space is often partitioned into several zones. We have, for example, player versus player battlegrounds, or barter areas, or exploration areas, and players have to be allowed to move quickly from one zone to another. So here, for example, a player wants to teleport in that particular area, and it has to wait for the message to be routed to reach it. The problem is that non-uniform peer distributions degrade routing performance in range query overlays. Now, why is it happening? Kleinberg showed that it is possible to add shortcuts to the graph of the overlay to enable polylogarithmic routing. So if the shortcuts of each player are chosen with a particular distribution, then the whole graph will exhibit the so-called small world property that enables the polylogarithmic routing. And it is very easy to build such shortcuts if the peer distribution is uniform. So here we have a simple example of a peer that has shortcuts in the overlay. However, building such shortcuts is challenging when the distribution is non-uniform. So there is basically a proof for that, but an intuition is that a player that is not aware of the distribution will miss some of the density hotspots while wiring its shortcuts. So for example, here, if we have a density zone, the shortcuts of the peer A will completely miss the density zone and therefore will not be a small world anymore. There is a known result that shows that with non-uniform data distributions, it is possible to build small world links, but only if the distribution is known to each peer, which is kind of challenging. Unfortunately, we have evidence of the fact that the distribution inside MMOGs, inside existing MMOGs, is highly imbalanced. Here, for example, a basic analysis we did on traces from Second Life, which is a popular MMOG. And so we divided the game space into cells and counted the number of players inside each cell. And what can we actually see is that there are a few cells that are highly overloaded, whereas the rest of them is more or less empty. And this is consistent with other studies that has been done for other MMOGs. So the distribution inside MMOG game space is highly imbalanced, which in turn degrades the routing process.
How many cells are you talking about?
Sorry?
Just to get a sense, how many cells are you kind of talking about in the last graph? Total number of cells.
If I recall, maybe 128 or something. Yeah. So our solution is to make the peers density aware. And on each peer, we will build a map of the density distribution. And then we will use this map to create density aware shortcuts that will enable small world property. There are several solutions to make peers density aware. The first naive solution is to locally collect all the coordinates of all the peers so that the peer will be able to construct that kind of distribution, in which each dot represents a peer coordinate, and then it will use it to estimate the density. However, this approach is not scalable because the overlays we are targeting are very large scale, so there will be probably many thousands of peers. And also, since it is peer-to-peer overlay, we have possibly high churn rates. That means that coordinates of the peers will be updated very frequently. So storing up-to-date coordinates of all the peers is not scalable. Therefore, we need to approximate the distribution. So for the approximation, we use a local quad tree that is local to each peer. So here we have an example of the non-uniform density distribution in which each dot represents a peer coordinate when we have two identified high-density zones. And on the right is the corresponding approximation of the density of the game space. And we can clearly see that here we have the two hotspots with high density clearly identified. And since it is an approximation, the density inside each zone is considered to be uniform. Now, first, when the peer joins the overlay, its local map is completely empty because it has no information about the density distribution. However, as it joins the overlay, it has direct neighbors inside the overlay and knows the coordinates of these neighbors. Therefore, it is able to locally compute the local density of the key space. So it adds this information to its local map. Then the peers share the local information to acquire a global state. We use two mechanisms to acquire the global state. The first one is that we are piggybacking density information to existing messages, and we are also using a gossip algorithm that propagates recently modified regions. And since this distribution is dynamic, because points of interest inside the game can change and objects can be created or removed, the density map inside each peer is able to adapt by overwriting recent information, overwriting old information when new information is available. The second step is to use the map, the approximation of the density distribution, to create small wall shortcuts on each peer. So a well-known technique to do that is so-called the log-partitioning, which consists in partitioning the graph starting from the coordinate of the peer into log n partition, and each inner partition will split the outer partition into half. So each time the distance decreases by half. And it has been proven that if the peer manages to partition the graph in that way and chooses one random peer inside each partition, then the obtained distribution of shortcuts will be a small world. However, to create these shortcuts, to use the log partitioning, we need either to have the whole graph or to accurately estimate hop distances to be able to create these partitions. So we use our map to estimate hop distances inside the graph. So a peer has its map and wants to estimate hop distance between A and B. It first finds the regions of the map that intersect the segment AB. Then it estimates the hops in each region. And since the density distribution in each region is uniform, estimating hops inside one region is straightforward. And then it sums all the results for all the regions to obtain a global estimation of the hop distance. Then this technique is used to sample the map in order to find the coordinate that is the farthest from the peer's coordinate in terms of hops. So the map is sampled with a system-defined number of samplings, and each time it does a sample, it estimates the hop distance to the sample. And finally, it takes the maximum as the farthest coordinate from the peer inside the game space. So here, the farthest coordinate is considered to be here because the peer has found that there is a big hotspot that is located in between the position of A and the coordinate, which means that there will be a lot of hops to reach this coordinate. And once we have this estimation, we approximate log partitions. That is, we compute the maximal distance inside the game space. So it is the distance between the coordinate of A and the farthest coordinate. And then this distance, then the map is used to find the distance that is halfway to the peer, then 1/4 way to the peer, and so on, which basically leads to approximate the log partitioning. This particular algorithm is completely done locally. So the only cost we have is the local computational cost of the sampling, which is a user-defined parameter. And once all this coordinate has been determined, the peer routes a connect message to each of these coordinates, and the peer that answers to the connect message becomes the shortcut of the peer. And if the distances, hop distances, have been accurately estimated, then the obtained shortcut distribution will enable the small world property. To evaluate our mechanism, we used simulation based on real data. So we implemented the whole system in the simulator, and then we injected real traces. We have various number of traces. We have latency traces collected from peers, between peers from the internet. We have churn traces from several systems that are peer-to-peer, or also corporate desktops. And for game density traces, we use traces that we derived from the Second Life avatar distribution. And we compared our mechanism in the simulator to different rewiring techniques that build shortcuts through the overlay. First, a very simple random approach, which has been proven to not enable small world polylogarithmic routing, and then 3 other rewiring techniques that are known to enable small world properties. First,
in the random uniform, you're just taking random from a set of nodes?
No, I'm taking random from the coordinates in the game space. So it means that basically the random will not be able to capture the distribution. The small world shortcut rewiring mechanisms. First, a mechanism that enables to log partition the space, but without taking into account the density distribution. So we create log partitions by assuming that the distribution is uniform. Then we compared to Oscar, which is a state-of-the-art system in which the sampling of the game space is done by random walks. And finally, the so-called optimal one, for which each peer holds the whole overlay graph, and so it is able to accurately know the hop distance to other peers. First, we wanted to know if our mechanism enabled small world shortcuts. So we evaluated the average route length in hops versus the overlay size compared to a simple logarithm function. And what we can see is that donut clearly exhibits logarithmic routing, which means that the links that the shortcuts that we create with our mechanism enable the small world property. A second important result is that donut, our contribution, is very close to optimal strategy. That means that the hop distances are accurate enough to be close to distances obtained by going through the graph. Basically, this is a very good news that donut is within 10% of the optimal. Then the next surprising result is that Oscar behaves pretty badly, sorry. And we hope that comes from the fact that it uses peer sampling that it uses random walk for peer sampling, and random walks behave badly if the underlying graph is not an expander, and we believe that the Delaunay graph, which we used for our simulation, was not an expander. So random walks led to a non-uniform approximation of the game space. Then we used our latency traces to estimate the latency of the routing process with an overlay size of 2,500 peers. And here again, we can see that Donut is really close to the optimal strategy and enables average routing within 300 milliseconds through the overlay. One might say that collecting the global state is expensive, so we estimated the bandwidth usage that is needed to propagate the global state. So we evaluated the consumption per peer during a whole week, and at the end of each day, we completely changed the distribution. So the coordinates of the hotspots were changing every evening. And here we can see that as the distribution changes, the mechanism struggles to acquire the new updated view of the distribution, which happens every day. And the main information of this plot is that the consumption is of only a few bytes per second per node, which is really low and may be considered negligible even for peer-to-peer systems with low bandwidth. We can see a slight increase of the consumption over the days, which we believe comes from the fact that the distribution complexifies since we are changing the hotspots. So old hotspots still haven't vanished, and new hotspots are emerging. So since the key space, the game space becomes more and more complex, the amount of information to exchange grows. However, at a certain point, if it becomes unaffordable to propagate the whole information of the game space, the precision of the map can be fixed. So the propagated information will be fixed with any distribution. So to conclude this first part, the contribution in peer-to-peer MMOGs are a completely decentralized technique to aggregate distributed game space information, which is really cheap because it costs only a few bytes per second per peer. And yet it is accurate enough because it can be used to build small wall shortcuts that are density aware, which improve state of the art by 20% and are 10% within the optimal. So this concludes the first part of the talk.
Can I ask you a quick question on the plot grid? Do you have any mechanisms to sort of actively prune out lower layers over time to stop the thing just generating very detailed?
Yes, basically because new information overrides old information. So at some point, if a zone has changed, the peer will propagate new information, and if before there was a deep part of the tree, it will overwrite and prune this part. Okay. Okay, so the second part will be on the work I'm doing now. So it's still a work in progress, so there won't be any results showing here. Still, I find that it is a promising work, so it's worth it to be mentioned. It will be on density-aware partitioning in server-oriented MMOGs. So we're not in the peer-to-peer context anymore. What we want is to partition the game space among servers, since the whole game space may be too heavy to maintain by a unique server. And when we partition, what we want is to first ensure fair load balancing, to not overload any nodes. And also, which is very important, we want to minimize multi-server range queries, because we have a low latency requirement on the range querying for MMOGs, and range queries that span over multiple servers will have higher latency. So we want to get all the range queries possibly on one server only. So we use range partitioning, as in the previous part, because it's a good choice for MMOGs, because it preserves data locality. The problem is that optimal partitioning depends on the current game state. So here is a simple example of a simple game distributions. Here we have 3 zones in the game and 3 servers to partition them. On the left, we have a bad partition. Why is it bad? It is bad because it partitions each zone between several servers. And more particularly, it splits this zone, which happens to be high density because of the game state, between 3 servers. And since it is a high density zone, there will be a lot of range querying inside because there are a lot of players. And all of these queries will span over 3 servers, which will incur bad performance. So a good partition of this particular game space would be to partition into distinctly each zone and affect them each zone to one server, so that this hotspot will be located only on one server, and range queries will be therefore very responsive. However, we can clearly see that this partitioning, the performance of the partitioning depends on the game state. So our contribution is to use density-aware partitioning. This comes from a simple observation. The simple observation is that most range queries are happening in 2 high-density zones, whereas the low-density desert zones have almost no range queries happening inside. So we would like to ideally do the partitioning only inside the low-density zones, without splitting the high-density hotspots. We currently have a prototype running on a cluster. We have the architecture is organized into a ring of servers, and each server is given a slice of the game space depending on its position into the ring. We have a coordinator that approximates the global density distribution of the game space and then maintains dynamic partitioning according to that distribution. To acquire a global state, each server samples the distribution of the partition that it is in charge of, and then all the approximations are sent to the coordinator. The coordinator aggregates this knowledge to obtain a global view of the game space distribution, and according to that, initiates load balancing. The load balancing partitioning mechanism is inspired by recursive bisection, which means that the game space is recursively split into slots, each slot containing approximately the same number of objects. And then each server gets a fair amount of contiguous slots. I said fair amount and not equal amount because the coordinator may choose to give more slots to one server if it prevents the partitioning of a hotspot. For instance, here we have a bad partition in which is perfectly load balanced because each server receives 4 slots. However, it is bad because a density hotspot has been partitioned between server B and server A. And on the contrary, a good partition would be to allow slight low imbalance because server C and server B receive only 3 slots and server A receive 6 slots. However, it is considered to be good because the density hotspot here is preserved, is entirely stored on peer on server A. So how do we avoid bad partitioning? The coordinator is aware of the global density distribution. It also knows the current load of each server. So it runs through the distribution, through the density distribution by trying to detect partitioned hotspots. And once a partitioned hotspot has been detected, like here, if if the servers that hold that hotspots are not overloaded, it tried to adjust the partition in order to avoid splitting the hotspot. So, for instance, it tries to affect the partition, the hotspot to the server A. And since it achieves that without overloading server A, it considers that the partition is good, so it applies that partition to the system. And here we can see that a rather significant load imbalance is allowed. Is allowed because the main goal is not to partition one of the density hotspots. But since none of the servers is overloaded, it is accepted. So this is an ongoing work. So we don't have any results yet, but we have a prototype, which is basically a distributed in-memory database, which is written in Java. It can be accessed through JDBC connector. On each server, we have a H2 in-memory database that is used to provide consistency to the range queries. We also have inter-partition queries, which are also kept consistent. We are now evaluating our system on Grid 5000, which is the French academical dedicated cluster. And also we want to use Planet Lab to simulate high client activity. And finally, we managed to contact a provider of a World of Warcraft server, which is a known and very popular MMOG, which accepted to log the activity from his server for us. So we are now collecting traces from a real World of Warcraft server with approximately 800 players playing at all the time. So to conclude my talk, we'll sum up the contributions. First, in the first part, I presented a scalable technique to acquire a global knowledge about the game space density distribution, which can be performed at low cost in a fully decentralized context. Then I presented a a technique to converge to a small world overlay with non-uniform distributions by using this global knowledge. And finally, I presented a system that allows density-aware partitioning that minimize interpartition range queries, therefore making them much more responsive. So the conclusion to the talk is that integrated real workload characteristics into the system is the key to impact MMOG design. Thank you.
So just to double check, in the first part,
Yeah.
you already use some other scheme that provides you with the Voronoi type of overlay with the locality, right?
Yeah.
So if you want to move just locally, there is no routing problem. You just move
Yes.
to the nearby. So essentially, this is only for teleporting, as you said, when you want to.
Teleporting, load balancing, and joins.
So why would it be for load balancing? You want to have it still Voronoi, no? I mean,
Yeah,
you
but
want it to be locally.
yeah, but if some of the regions support is becoming overloaded, we might choose to take an underloaded node and join it to this position in order to support the whole hotspot.
And in that case, how does this help you? You need to route everything from that hotspot to this, or part of the things from the hotspot to that node.
We have to locate an underloaded node and then route it to the overloaded zone.
And that node might be somewhere.
Yeah, sure.
Okay.
It's probably on a desert zone somewhere opposite.
And how often does that happen in practice? Do you have any idea? I mean, you show what is the advantage, how faster your routing technique is when you decide that you want to move something. But in practice, how often these events like teleporting or load balancing happen? Do you have any idea?
I don't have numbers, but players often move from a zone to another if they want to fight with each other or if they want to just trade. So they have to move from one zone to another. And also, there are some crowd phenomena that can form if there is a battle. So a zone can become rapidly overloaded. So it will need fast load balancing.
And then a related question, so you use some kind of overlay algorithm underneath, which essentially will give you some partitioning, okay, depending on what it does with these things. So when you evaluated these dynamics, you said that you were changing zones overnight and so on. Did you take into account the actual behavior of the underlying overlay algorithm and how it affects the distribution of nodes?
Basically, we only took into account the peer distributions. So with natural churn from our traces, peers disconnected from one hotspot and connected to another. So the peer distribution were naturally non-uniform because of that.
But you could have some bigger effects, correlative effects, as you said, if you have a crowd event, that everyone moves to one point, so you would have something which is more, changes the entire thing at the same time, as opposed to these turning on and off. So you could have a bigger change in topology. How would that reflect the convergence of your routing gossiping algorithm?
I think we would see a peak of the bandwidth since the map struggles to adapt. So, yes?
Yes, so first just to clarify, so you're essentially moving, when you move to a new cell, you essentially want to communicate with the coordinator of that cell, right?
Yes, that's the slide.
So, so why do you need kind of multi-hop routing? Can't you just have one hop direct routing? And then you mentioned that the number of coordinators are on the order of, let's say, maybe 150, right? So is it that big a problem to maintain information about all the coordinators and just
in the first
one-hop routing?
in the first part, we have a peer-to-peer overlay, which basically has many thousands of peers. So,
But how many coordinators would
But the coordinator, I'm sorry, that might be a misunderstanding. The coordinator is only for the second part of the talk, which is non-peer-to-peer. We have first part about peer-to-peer system, which is completely decentralized. And then on the second part, we have a server-based system with coordinators.
So when you move to a new cell, you would talk to any random node in that cell as an established connection, or you would only go to some kind
I have to find the coordinate. I have to find the peer that is responsible for that cell.
Yeah. So I mean, what do you call that node who's responsible within that cell?
It is done by greedy routing. So I want to move to a particular coordinate. So I route a message with this coordinate. And the overlay greedy routing enables that the message will arrive to the peer that is the closest to the coordinate, which is basically the coordinator of that node.
Okay, maybe we can take this off.
Okay. Sorry.
So I have a quick question about the dynamic partition, the second partition as well.
Okay.
So you're doing this in a circular namespace and you're making small changes. Did you see sort of oscillations in behavior? Or what's the stability like?
For the moment, it's under evaluation, so I don't have any precise results. But we're
But it seems like one change could kind of roll away, come back again, just carry on.
we might have to move several partitions for load balancing.
I'm actually curious what happens if like bunch of people in one zone moves across the boundary to the other. How use I would be a
For which part?
the second part.
So if
Like today, teleport to the other server altogether, or would they be like continuously migrating towards the other server?
I'm sorry, could you?
So let's say you have a bunch of like people in same zone. They're very closely located, but in high density, and move across the boundary of the zone.
Yeah.
What happens in those cases? Like how your
If a player moves from one zone to another?
yeah, like a bunch of people all together move from one zone.
Like an army. Like
Yeah. Oh, in that case, it depends on the time it takes for the group to move. Because if we have a crowd phenomenon with a lot of users gathering together to move somewhere, if they stay together for a long time, the coordinator may identify it as a hotspot and try to move a server to accompany the whole crowd. But if it's a fast phenomenon, so just people crossing, well then it does not incur movement of partitions.
So I think that's actually a case where you see a lot of lags when you play MMOs.
Yeah.
You don't have any evaluation.
We're still waiting for our traces. They are currently being done.
I had a question about how specific are these partitioning techniques, the server side of things, to have in a coordinate space? Could some of it is generalized to, if you didn't have an actual coordinate space imposed by the application, but you just had access patterns where certain things were accessed together? Would you use a similar approach, or is it really based on a coordinate space?
For the moment, this really targets MMOGs because we have identified specific workload patterns, so we are addressing these. But that might be used for pop subsystems, or yeah, why not?